We'll start in a couple of minutes. I think people are still joining. But in the meantime, hope you can hear me clearly and see my screen. If not, please drop a note on chat. Okay, let's get started. People can join in a little later as well. So welcome to the week 5 live session of the CS104 course, and let's quickly go over this. So this will be a 2-hour session today, and we will do a recap of this week's course content followed by some problem solving which will help you solve assignments. And since we can have multiple people on the call, all interaction will be through the chat box. So please use it in case you have questions, in case you have comments, in case you don't understand something clearly. Please feel free to ask. No, don't hesitate. And after the session, you will get access to the slides and the recording. Yeah, that's about it. So how we'll do the 2-hour session is we'll have 45 minutes of recap, basically till about 7:50, and then we'll have a 45-minute problem solving towards the later half of the session. In between around 8 we will have a short 5-minute break, and we usually have enough time for doubts and questions. So feel free to ask, right? That's the point of the session. So let's get started. So let's start with questions that people asked in the previous couple of weeks. I think there's one from week 3 as well. But yeah, one question I got was, what is top N error, right? So this is an error metric for classification, right? So when you have neural networks that broadly do the task of classification, they tell you whether, let's say you have an image, they tell you whether it belongs to class cat, class dog, class horse, and a bunch of other animals. So the output of these neural networks typically is, let's say we have 10 classes, right? In our previous example, this 10 represents the 10 different types of animals maybe. So your classifier will have outputs corresponding to all 10 of these, right? But those outputs will typically be a score or a confidence value. Let's, for simplicity's sake, say that this is some kind of a number that's very similar to probability, right? For instance, let's say it thinks with 50% confidence or 0.5 confidence value that it's a cat, and then it might think with 30% confidence that it's a dog, and 20% confidence with as something else, right? And maybe this is 0.19 and there are a bunch of 005, 001 and so on, right? Now one way to see if you got the right answer is to take the class which had the highest probability. In this case that would be 0.5, right? And let's say this class belonged to cat, right? So you would say, okay, the classifier said that the answer is cat. Does that match my actual class of the image, right? And suppose it matches, you say this is correct, and let's say you run this 100 times and you see how many times out of 100 is it correct. That's one way to do it. Now think of top n as a kind of relaxed way of doing this. So if I said top 1 error, right, basically this is what it would be. But in top n, let's give this n a value of 3. Now what I would do is I would see in my top 3 guesses of the classifier whether the correct answer is there. So let's say the top guess was cat, the second guess was dog, the third guess was horse. So now let's say my image actually belonged to type horse, right? So then it is not the first correct answer or the second correct answer, but it is the third correct answer, right? So if I'm looking for top 3 error, then I wouldn't, if I'm looking at top 3 error, then I wouldn't consider this wrong, because in the top 3 guesses of the classifier, the correct class is still there, right? But let's say instead that the image was maybe a cow and your classifier said cat, dog, horse, right? And maybe the fourth answer was cow. Then it got it wrong because none of its 3 answers had the correct class, right? So this is an example of top 3, and this n can take any value, right? Typically you would see top 5 or maybe even top 10 being used, right? So ultimately what you do is you take the percentage of times the correct answer was not in the top n guesses of the classifier. So this is in a way a relaxed form of calculating error. Rather than saying I'll take the output with the highest probability or confidence value, we relax it to consider more outputs of the classifier. Okay, is this clear or any questions? Feel free to ask if it's not clear. Any other questions apart from this? Something that you didn't understand in the course? We are almost halfway in the course, right? 5 weeks are complete, and I think even the 6th week's content is live. So any other questions, anything you don't understand or anything you find particularly difficult, feel free to ask about it. I'll wait for a few seconds here in case someone has something to say. If not, we'll continue. Okay, if there is nothing, let's move forward. So another doubt somebody had asked me was, this wasn't a doubt, but this was a request to have questions with involving basic CNN fundamentals, right? So I've put in one here, and I've also put in a link to a presentation which has a lot more of these numericals. So you can go take a look at that offline if you're interested in this. But from the perspective of this course, I don't think you need this. This is just because somebody asked and maybe that person had doubts on CNN fundamentals, right? So that's okay. So if you want to look at more, please go visit this link. So this question says, consider a CNN which has the following layer, which is a convolutional layer with 64 3x3 filters at stride 1, padding 1. The dimensions of the input image is 3, 224, 224. What are the height and width of each image in the output image volume of layer 1? So you are given the input, you are given layer 1. You are asked what is the height and width of each image in the output volume of layer 1. You have 4 options. I'll give you a minute to maybe work this out, and then we can take a look at the answer. If you work it out and you get an answer, please feel free to post it on chat. If not, we'll take a look at the solution anyway. Okay, let's take a look at the answer. The answer is 224 into 224, so it remains the same, the height and the width, but how that is more interesting, right? So here is the formula that will kind of tell you. So if you had to calculate height, you would take height of the input image minus f, right? This is the size of the filter, plus, so typically filters are square, right? That's why, and we consider one dimension and then everything else remains same. For instance, here also you'd see that, right? So if I calculate height, the width looks exactly the same. So minus 3 plus 2 star p, so p is the padding and padding is 1. So 224 minus 3 plus 2 divided by stride, and stride is also 1. So you get 224 minus 3 plus 2, which is 224 minus 1 plus 1, right, which goes to 224. So the overall height of the image is 224. Now you might be wondering from how do you derive this from first principles, right? So you can actually try and do this. Think of a very simple image, right? Maybe something like 3 cross 3. And now consider a filter that's 2 cross 2, right? So the filter starts here and then it moves one step and then it moves to the next row and then it moves to the next row, right? Something like this. So you can kind of calculate the output sizes based on this. Now if I add, so this amount by which the filter moves is called the stride, right? So the stride in this example was 1. The stride could have also been 2, right? So, and that's the definition of the stride. Then further you have something called padding, which is typically, if I say padding equal to 1, I mean that I will add one row of zeros, typically zeros, one row of zeros and one column of zeros, right? So this is done on the boundary of the image. So you can also, first you can calculate with just a filter size, see if you intuitively can come up with this expression. Then consider incorporating stride, right, a non-1 stride. So try to move the filter by maybe 2 and then see what happens. Can you come up with that expression? Then finally incorporate padding and then see if you can come up with the final expression. So rather than blindly remembering this as a formula, I would encourage you to come up with the derivation. It's not very difficult, right? So that way, even if you forget what this is, you'll be able to figure it out. So that's the explanation. So you'll get the exact same calculation for width as well. So the dimensions of the output image is 224 cross 224. So with this, yeah, we'll move ahead. So I've included only one numerical because it's not really in the scope of this course. But if you want more, feel free to go take a look at this. Okay, so next we will look at dragonfly topology, right? So again, like I said, this is based on a research paper, so it's kind of very hard to go into the details without spending half an hour. And spending half an hour on just this concept is completely outside the scope of this course. So I'll try to introduce it as simply as possible, and I've given you a link to both the material I have used to explain these things, as well as additional references that you can go look at, right? So feel free to, in case you're curious. So these additional references will also have maybe some simpler topologies, right? For instance, you might see things like a star, a mesh, very common topologies, and things like a tree, where in the higher level you have network elements or routers, and in the lowermost level or the leaf nodes of the tree is where you actually have the compute nodes, right? So you'll see all of these topologies here, and I've tried to find the easiest and most accessible resources. So you can take a look at this and at least look at the shapes of all these topologies, right? So if you, at a high level, why do we need all of these topologies? Broadly, it is, one is the performance of the network, right? Interconnection network. So we measure that mostly by latency, also by throughput possibly if needed. And next we would come to cost, which is directly proportional to the cable length, right? So that's another parameter to consider. And then things like diameter also plays a role, and that kind of affects both the latency and the cost, right? How from one node to another, how many nodes you have to go through, or what is the length of the communication path, things like that are affected by these things. So at a very high level, you want to have a very high performance network while also trying to minimize the cost, right? This is the motivation. So dragonfly also is one of those topologies. Again, each of these topologies will try to do something specific to achieve these goals. So you can ask yourself while you go through these slides as to what it is that this topology does that's very unique to itself, right? So let's take a look at dragonfly broadly. So as one of your assignment problems I had mentioned, dragonfly is a hierarchical network with 3 levels. Those 3 levels are router, group and system. So if you take a look at this block diagram, right, so you will see a bunch of routers here, and some of these routers are connected. You can see something called intergroup interconnection network, right? So this whole square forms a group, as you can see here, and the whole thing forms a system, right? So that's the hierarchy. It's if you go from bottom up, it would be router, group and system. If you come from top down, it's system, group and router. And again, there are some details such as how routers within a same group communicate, that's through something called local channels, and how routers communicate to routers in other groups, that is through something called global channels or possibly terminal channels, right? So you can look through these things in detail, but you don't really need it from the perspective of this course. Knowing this much, the first line definition of dragonfly is good enough. Okay, so that was the doubts part of previous sessions. So let's start with this week's recap. So this week we broadly looked at an introduction to TensorFlow. So we looked at various things like how do you build a model or how do you specify a model in TensorFlow. Then we looked at training a model in TensorFlow. We looked at the tensor data type. We looked at distributed training, and then we looked at some optimization such as the XLA compiler and the high level optimizer again of Excel. So let's get started with that. Right. So last week we looked at PyTorch, right? So you might be wondering, and you should ask yourself this question, right? How do TensorFlow and PyTorch really differ? And a lot of features that you will see today or broadly in week 5 will help you answer that question, right? How do each of these things define networks? What kind of features do they provide? How easy is it to do something in either of these frameworks? But broadly, one difference that prominently remains is PyTorch has seen a lot of adoption among research communities, and TensorFlow remains the primary thing for industrial deployment, right, or for productization. So that's one thing. But you can ask yourself why that is, and if you can map some of these features to those reasons. Right? So, from the perspective of training, TensorFlow offers various ways to design a model, one of which is using Keras estimators. From the perspective of data, you have TF datasets, and you've seen a lot of functions and parameters that you can use with TF.data. Then further, in the training space itself, so broadly this is divided into training and deployment / inferencing. The other thing that TensorFlow has is a distribution strategy that helps you kind of train either on CPUs or on GPUs or TPUs. You can also distribute it along multiple GPUs, possibly multiple TPUs and CPUs as well. And then if you want to analyze your training workload, you have TensorBoard, and I think you've seen some visualizations with TensorBoard. And between training and deployment, you see a couple of things, right, which are maybe common to both. For instance, the model repository or TensorFlow hub may be one place that you get pre-trained models from that you can use for maybe inferencing, or you might take that model and do some amount of incremental retraining or transfer learning, as you will see in the next week, and you might use it, right? So this is common to both. And similarly, you can take a model that you train and you can serialize it in order to save it, right? And then when you want to use it or deploy it, you can deserialize it and run inference on it. And on the inference side, again, you have TensorFlow serving, which is for model serving or inference purposes. And you have a separate variant of the framework called TensorFlow Lite, which is intended for mobile or edge devices, things like Raspberry Pi or your smartphones with Android or devices with iOS. And again, here you have TensorFlow.js, which gives you visualizations on the browser and things like that. So this is broadly what TensorFlow offers. And again, I'm sure you've seen TensorFlow 1. something and 2. something and some of the differences, right? So one of the primary differences that comes in 2.x is eager execution and easy model building with Keras. A bunch of the other things are always there, so I don't think that those things are very specific to 2.2. And then there was a bunch of work on simplifying the APIs, cleaning up deprecated APIs and things like that, and data loading and Keras model building, again eager execution, TensorFlow hub, and distribution strategies for distributed training, and support for all hardware accelerators, CPU, GPU and TPU, and then exporting it, as we saw, right, to having the saved model as an interchange format. And finally, TensorFlow datasets. So this is what TensorFlow 2.x offers you. Now, coming to model building, we have various ways in which you can do this, right? So you will see many frameworks or many system software tools offering this, because different people in different parts of the development chain might need access to different knobs or different levels, right? So for instance, if you just want to do something very simple, you want to use very simple models and you're a new user. Suppose the framework told you that you had to write everything from scratch. Let's say you're trying to implement a very simple CNN, right? Something like what we saw in the last class that did classification, digit classification on the MNIST dataset. So let's say you were trying to do something like that, and TensorFlow said that you had to write everything from scratch, right? You are very likely going to say, oh, let me use PyTorch. I can't do all of this to just build a simple CNN. So that's one reason why there. So that's a reason why there's functionality offered from the perspective of different users, right? It could be a user who is very new, just trying to get something running, or it could be a researcher who is trying to build something very, very different, right? So there is support for different levels of users. So typically new users use the sequential API, which has built-in layers that you can use to define a model. One level below that, right, is maybe engineers with some standard use cases. So they use the functional API with some built-in layers. Then if you need even more control or even more visibility or even more tweaking thing, then you would use the functional API with some custom layers, custom metrics, custom losses. And then finally there is a level of expert user or a researcher who writes everything from scratch, right? So there's support for all of these levels. So this continues on the same thing. So you see sequential API, which defines it as a series of layers. Then there is functional API, which allows you to do slightly different things. And then there is model subclassing, where you have to write everything from scratch. Yeah. So again, in the training thing, you see something very similar. So model.fit is a very quick experiment. If you need one level more control, then you use fit with callbacks. So again, you could have things like checkpointing, early stopping, monitoring, things like that, but nothing very different in the model training itself. Then you could also want to use a different optimizer, different loss function, etc. Then it gives you again one more level of customization or visibility. And finally, if you want to do a lot of different things, if you want to modify a lot of things, then you have gradient tape, where you can build yourself a complete custom training loop. So you could do things like a new optimization algorithm, modify gradients, etc. Okay, so with this we move to a slightly different topic. So this is caching, right? So you're doing a lot of pre-processing here. What is pre-processing? Why is it needed, right? So let's say your neural network takes input of some dimensions, right? And let's say your image is of some other dimension. So here's a simple pre-processing that you need to do. You need to resize this image so that it can be fed as input to this neural network. If you try to feed something that is not the default input size, then the neural network will not accept it, right? It will likely throw an error. So you have to resize your input image. That's a very simple pre-processing example. But now what this does is it adds one more step. So there is fetch or IO that you do in order to bring the data from your storage, right? So the data is in your storage, you bring it to memory, and at this point you do your pre-processing, and then you perform training or inferencing on this data. So now if you so here what you can say is you can ask for this data to be cached. Basically, after you do your resize, you can ask TensorFlow to cache your data. So when we say cache, what do we mean? This data will remain in memory, right? Because training is a very iterative process. You iterate through this data for one epoch, then you again iterate through it in the second epoch, and so on, typically hundreds of times, right, till you attain convergence. So that's one reason why you would want to cache. Now here's a question: why would you choose to cache here after the pre-processing step rather than right after you fetch it? Any answers to this? Just curious. It's all right if you don't know, but if you can think of the answer, that would be interesting. lower latency. Right, that's definitely one reason you do it. So let's say if you do it here, right, if you cache it in memory right after you fetch it, you will eliminate the fetch process anyway. The next time you want to work on the same data, it will be available in memory. But after that, you still need to do the pre-processing, which again adds some time, right, before you can actually train with that data. So definitely caching here will give you a benefit in terms of time. It would give you, from the perspective of training, we care about throughput, so it would give you higher throughput. But another thing that's very important to consider about caching is, are your pre-processing functions suitable for caching? So I'll give you two examples here. One is something called a random crop, right? So if you take an image, one of the things people do while training a neural network is to crop the image at random places, right? So that this is kind of to avoid overfitting or to make the neural network more generalizable. So it learns to recognize a dog maybe from its face, maybe also from its tail, maybe from its body, right, at various crop positions. Now this is something called a random crop, where what we do is in two different epochs the same image would be used, but you would crop it at different places, right, because it's a random crop by definition. Then you cannot really cache it, because the next time the pre-processing is essentially something very different, right? So you can only cache it if the pre-processing is an operation that is suitable for this. Second example is, let's say you have something like an audio or a video input, right? So typically this is compressed or encoded and stored in some format. So there the pre-processing step will actually involve a decoding or decompressing, right? So as a result, the file that you have, let's say the file was maybe 1 GB and now the file becomes 4 GB after you decompress it or decode it, right? So that means that you pay for this latency or throughput benefit that you get. You are paying a price in terms of memory that it takes to cache it. Now let's say you have a 256 GB RAM available on your system, then it's perfectly fine to use an additional 3 GB. But let's say you're running on an 8 GB RAM system and your model training itself takes up a significant amount of memory. Then this might be critical and you might actually prefer caching here, right? So this is an important thing again to remember, where after which step you cache depends on again your system, your workload and things like that. Right, so this again reiterates some of those things. Why your input pipeline is important. Data might not fit into memory, something that we just spoke about. Again, might require randomized pre-processing, basically repeating whatever I said. Efficiently utilize hardware, maybe we didn't speak about this, but what it essentially means is, if my pre-processing and fetch take a lot of time, then my GPU is going to be idle, right? It's going to be waiting for this mini batch of data to be ready so that it can train on it. But all that time that it spends waiting is time that you're not utilizing the hardware efficiently. It's idle time. You don't want that, and that's why you try to do some of these optimizations. So if you cache the data, then your GPU doesn't have to wait for the fetch, doesn't have to wait for the pre-process, right? Something like that. And again, the other reason is you want these loading and pre-processing to be decoupled from the computation itself. You want these to happen independently. Because if you think about it, right, while one batch is computing, there is no reason not to fetch the next batch and pre-process it, right? You can do it in parallel, right? So you decouple these two things essentially, right? So this is broadly what is called the ETL pipeline. You will see it in a lot of places, not just here. So broadly the extract is reading data, parsing the file format. Transformations, again we saw various examples. It can be image transformation, it could even be shuffling or batching and things like that. And loading is when you finally transfer data to the accelerator. So this is the pictorial representation of what we were talking about. I don't know if this is very visible. Let me try to increase it a bit. Okay, so it's blurred, right? It's probably the screenshot I took from a very low zoom, right? I didn't realize it was this blurred. But anyway, you can find the original slide in your course lecture, so that's okay. So broadly, this is, in case you can't read, this is open, read, train, right? And this is your epoch time. So here you kind of fetch the data and you read it and then you train on it. So you can see this happening very sequentially, right? Which is a very naive way of doing it. Like I said, this compute needs to wait for this read, but there is no reason for this read to wait for the previous compute to finish. You could as well have started this here. You're wasting time by doing this blind, right? So one level of optimization is this, right, where you do it here, and this is called prefetching, where you fetch the data ahead of time. You can also do a lot of, again, caching is something we discussed, so we won't go into it. Again, you could have something like a map operation, some kind of, think of it as a pre-processing operation itself. So again, this says apply time consuming operations before cache, and we discussed in very much detail as to why that is needed, right? So once you cache it, you will see things like this, right, where these are completely eliminated. There is none of this needed. It's just fetched from cache and trained. So that reduces the overall time, epoch time also. So this was about your whole input pipeline and fetching and pre-processing and things like that. You'll find slightly different terminology, right? Things that I might call fetch might be referred to as read, and pre-processing in different places might come with different terms, but broadly you get the idea. So any other questions before we move on to distributed training? Any other parts that were not clear? I'll just wait for a few seconds before I proceed. Okay, if not, let's proceed. So again, why distributed training? So this slide shouldn't have been called why distributed training, because we discussed that in detail in one of the other sessions, right? For instance, we said your model might not fit in GPU memory, or you want to train faster by parallelizing data, and we discussed the various ways in which you can do that: model parallelism, data parallelism, etc. So here we are talking about TensorFlow training, and what are the goals for TensorFlow distributed training, right? So broadly, you will see these goals for any framework. You want it to be easy to use. Basically, the person who is making those changes or who's writing this distributed training loop shouldn't have to do a lot of code changes. Let's say you had a piece of code and it was running on one GPU. It should be as simple as setting a flag and have it run on multiple GPUs, right? That's something you need. Second thing, of course, you need is, even though you have minimal code changes, you want great out of the box performance, right? And thirdly, you want it to work with different architectures, hardware and APIs. So for instance, I might be doing this on GPUs, and then I might say, okay, I have a TPU, how can I try out the same code on this? right? So all those things are desirable from the perspective of a framework. So these are goals for TensorFlow's distributed training, and broadly it aims to be an easy way for distributing TensorFlow training. And yeah, so use cases of this TF distributor strategy. Again, you should notice that TensorFlow has multiple of these options, right? For instance, I think we looked at mirrored strategy, and we looked at one more for the TPU distribution, right? So we have different variations of those strategies, and again you could do this in different ways, right? You could come up with a new strategy, or you could use the Keras or estimator API to distribute your model, or you could use a custom training loop. You could do all sorts of things, and again TensorFlow offers you different API services for each of these. And here's a very simple example. So you have multi GPU all reduce synchronous training. So again, you'll in a lot of places you will see this synchronous and asynchronous, right? What it broadly means, synchronous means that they will exchange data after at the end of, let's say, your batch boundary, right? So yeah, this is exactly it. So they synchronize gradients at every step. Asynchronous, on the other hand, does not do that. So asynchronous has some impact on your convergence and final accuracy because of this. Synchronous, because it synchronizes gradients at each step, is basically it does not affect the accuracy or the convergence side at all, right? And all reduce is again a very common thing that you'll find throughout HPC. It's a very efficient way to aggregate gradients. So with that, yeah, mirrored strategy was one of the simplest things that you could do. So you can see how simple it is here, right? If you want to do this on multiple GPUs, you say mirrored strategy device is equal to 0 and 1, and then you say mirrored strategy cross device op equal to NCCL all reduce. So this is again how you are aggregating your gradients. So this is as simple as it gets to do distributed training. So that's all we had about distributed training. We are at 7:45. Let me just see how much more of recap I have. We'll try to finish recap and then take a break. Meanwhile, any other questions, doubts? Yeah, we have a few more slides, so I think we can continue till then and then take a break. So TF dot function, right? This is another thing that you'd see used. Remember this even for the next week's set of lectures. I think you will see some more things that you can do with this TF dot function. But broadly, it does a bunch of graph rewrites, or you can think of it at an even more high level as optimizations that it does to your computational graph. And this is runnable without Python. So with that, we will transition into XLA, which is a linear algebra compiler that supports multiple backends, right? GPU, CPU, and TPU. And again, this operates on what is called HLO IR, right? So this IR stands for intermediate representation, and that's what this compiler uses to operate on. So you can see here there is HLO, and there are some optimizations that are performed, and then there is some code generation, and then finally there is some backend, right? You don't need to know too many details about this. Again, fusion is something that you will see in a bunch of frameworks, in a bunch of libraries. For instance, if you look at TensorRT, right, which NVIDIA gives for accelerating inference on NVIDIA GPUs, you will see that TensorRT does what is called kernel fusion. And even if you've studied CUDA, you will see a lot of mention of kernel fusion, right? The way you write kernels itself can have a huge performance impact. So if I write something like this, let's say this is kernel 1 and kernel 2, this is all assuming that I'm writing in CUDA. Instead, if I could write them as kernel 3, one single kernel, many times I would see a performance benefit. But now remember that we are operating at the level of frameworks, right? You only write a TensorFlow model or a PyTorch model, but you still want to benefit from all of these lower level optimizations without actually doing them yourself. So the frameworks typically take care of these optimizations, and they do them behind the scenes. So TensorRT that I mentioned also does automatic kernel fusion. XLA is also doing that, and broadly, like the name says, it combines different computations together. As a result, the memory bandwidth is reduced, and you can see an example here, right? There is a multiply and add that is written as a MAC, right? Because each time you have something like this, there is additional bandwidth that comes into play. Yeah, so using XLA from TensorFlow is as simple as saying as add tf.function JIT compile equal to true, right? So JIT stands for just in time compilation, and here again you see a flow between the TF runtime to getting the executable. And yeah, we'll skip past this. Now the interesting part here is that you can only compile certain blocks with XLA, not everything. And I think that was 500 out of 1500 or something like that, right? Those operations. So certain things are supported, certain things are not supported. So how do you figure out which of these are supported? One thing you can do is to rely on a profiler, and the other thing you can do is to identify many smaller kernels. So let's say I have a bunch of kernels, right? These lines are kernels, and let me kind of take a worst case example where all the alternates are XLA compilable. So now what I do is I identify that all of these are XLA compilable by whatever means, and then I use a add tf.function JIT compile equal to true. But this wouldn't be as good as, let's say, 3 that I can directly you compile and have as one block, and maybe 3 that I cannot compile at all, and again 2 that I can compile, right? So in general, larger blocks that are compiled mean better performance. Again, because you will have overheads every time you transition out and go back, right? Things like that. So the challenge is to identify these blocks, and again, you will see this with a lot of features, right? There is this pattern where you have a feature, and one level of flexibility that the framework gives you says that you as a user can figure out what you want to do. For instance, here you can use this to identify which blocks are XLA compatible, and you can use this to compile them. That's one level. The other level, which is more commonly preferred by most users, is that the framework does this for you automatically, and you just need to use some flag of some kind, right? So every framework, for most features that it offers, will try to do something like this. So you'll see auto clustering, automatic mix precision, a lot of auto tune, a lot of things like that, right? So what does auto clustering do? So it finds and compiles the largest cluster, and you as a user don't need to make any change, right? All model changes are handled by TensorFlow's auto clustering. All you need to do is have this environment variable set, or you can do this tf.config.optimizer.set_JIT auto clustering. As simple as that. But this comes with some caveats. I think we had that in one of the slides, that the performance that you get might have some weird cliffs and things like that. So yeah, there's always that. This I think I already mentioned. Out of the 1500, 500 are compatible. Uncompilable, so in case you put uncompilable ones inside the JIT compile equal to true, you'll end up with a runtime exception, and you'll see the stack trace for that op creation. Okay, with that we are at the end of the recap session. So I think we are a little ahead of time today. So, but we can take a break and then continue with the problem solving. But before that, I'll give you a minute to ask any doubts or questions from week 5 content, or even week 1 to 5, right? Any questions, any doubts, feel free to ask. I'll wait for a minute. And then we'll take a break. Books for clearing doubts related to TensorFlow and Keras. I would have to look for a book. I'm not aware of any of them, but I can do that and get back to you. But typically, what people do is TensorFlow has a lot of official documentation, examples, blog posts, right? So, on most features that you will see mentioned, there will be a detailed blog post with hyperlinks, with examples. That would be a good starting point to understand those features, right? Other than that, you might find ML application books, right? Like I've heard of things like ML cookbooks and things like that are either written in PyTorch or TensorFlow, and those will give you some hands-on examples and things like that. But broadly, for TensorFlow features, I would recommend starting from the TensorFlow site, looking at the blogs and things like that. Does that help? Okay, great. Any other questions? Okay, if not, let's take a 5-minute break. It's 7:55, so we'll resume at 8 o'clock. I'll stay on the call, but we'll continue at 8. Feel free to take a short break and come back. Okay, let's continue and move to the problem solving part of this week. So let's start with the first question. Which of the following is the default execution in TF 2.0? Lazy execution, eager execution, graph execution, none of the above. C, graph execution. Okay. C, graph execution. Okay. Graph execution. Okay. Any other answers? Okay, let's take a look. The answer is eager execution actually. So again, although you might associate graphs with TensorFlow, uh, these lazy and eager executions are common terms that you would uh, find, right? So what does eager execution mean? So it basically means that operations that you define are evaluated immediately, right? It is in fact the opposite of a graph execution, where if you remember in TensorFlow 1.0, what it does, or 1.x to be more precise, what it does is it takes the operations that you define, build a computational graph out of them. So there is this compilation sort of a step at which you get errors and all that, and after that this graph is actually evaluated and you get results, right? So this is called graph execution. It might also be referred to as lazy execution because it's not evaluated immediately, right? It's evaluated after you build a graph. Whereas in TensorFlow 2.0, one of the big changes that came about was eager execution that made it very similar to PyTorch or Python. This is how PyTorch by default does things. So it takes things that you define and immediately evaluates them. So one thing is you might not be able to get compile time errors and things like that, right? So this is eager execution. So is this clear now as to why the answer is eager execution and not graph execution? Great. Let's move to the next question. For new users whose aim is to build simple models, which of the following model building can be used? Sequential API, functional, functional plus custom, subclassing. Any answers? Okay, B, functional API, A, sequential API plus built-in layers, A, sequential API plus built-in layers. Okay. Okay, let's take a look at the answer. So it is A, sequential API plus built-in layers. So why not B. So C is, I think C and D are ruled out, right? Subclassing is for someone who wants to write everything from scratch. That's not for somebody who wants to build simple models. And functional API plus custom layers is also similar, right? You want to have customization there. So that leaves out A and B, right? And these are close enough, right? So this is for people who have who want to use simple models with by defining some built-in layers. You could also use functional API, but again, because it specifically mentions new users and simple models, the closest fit to this question would be sequential API plus built-in layers. Functional is a close enough answer. It's for a slightly more advanced class of users. That's the only difference. Is that clear? Okay, let's move to the next question. Choose the wrong statements about symbolic API. Your model is a graph of layers. TensorFlow helps you debug by catching errors at compile time. Your model is Python bytecode. And you have various combinations of these as your options. Maybe D, only 3. C, 2 and 3. Okay. Any other answers? Okay, let's take a look at the answer. It is D, only 3. So I think one person got it right. So let's take a look at this, right? Symbolic versus imperative API. So in your symbolic API, your model is kind of a graph of layers, and TensorFlow. So this is basically where you compile, right? So again, going back to the earlier thing, you can think of it as lazy execution versus eager execution, right? So here there is a compilation process in the symbolic API. In the imperative API, there is no compilation. It is Python bytecode, so that means that you don't get errors at compile time. So it's harder to debug in a sense, but you have complete flexibility and control because you have subclassing and you can define your own thing, right? Now let's take a look at the answer. Symbolic API model is a graph of layers. That is correct. TensorFlow helps you debug by catching errors at compile time, which is also correct. Model is Python bytecode. No, model is not Python bytecode. That is in imperative API. So D is 3 is wrong. So D is the correct option. Is that clear? Okay, let's move to the next question. What is the functionality of tf.data.autotune? Tune the value dynamically at runtime, tune the value statically at runtime, dynamically at compile time, statically at compile time. Take a minute to think about this. B, statically at runtime. Anyone else? B, tune the value statically at runtime. Okay. Let's take a look at the answer. It is A, to tune it dynamically at runtime, right? So what do we ideally want this to do, right? So if it was statically at compile time, it's not very useful, right? You want the highest flexibility, basically that it does it at runtime and it does it dynamically, right, regardless of what the input is. So what does this actually do, this knob? The number of elements that are needed to be prefetched should ideally be equal to or greater than the number of batches consumed by a single training step. So if you think of this logically, you will realize that this condition means that your hardware will never be idle. So one option is, again, like I told you previously, that you'll see this pattern in a lot of places. A user could manually tune this value or just set the value to auto tune, which will then prompt the runtime to tune the value dynamically at runtime. So it gives you the most flexibility through this option by tuning the value dynamically at runtime. That's the functionality of auto tune. Hope that's clear. We'll move to the next question. Oh, this is not clear. Okay. So is there a doubt about the other options, B or C or something like that? What exactly is not clear? Can you tell me so that I can explain better? A option is not clear. Okay, let me see if I can find an example quickly. So let's say I can't find an example, but let me try to come up with an example, right? So let's say in a single training step, you consume maybe 10 batches, right? And you want to prefetch either this 10 or something greater than this 10, right? So now what I could do for a given data set is to set this value to 10, So that would be depending on what APIs I am using. I could either set this at compile time or at runtime, but this value is statically set, right? So these would be the two things in case I did that, right? That is not what auto tune does, because this 10 might work for a certain data set, it might not work for other data sets. So what auto tune needs to do for you is to give you the highest flexibility by not making this value static. This value needs to be dynamic. Additionally, if there is a compilation step, this value need not be set at compile time, it can be set at runtime. Again, why does that give you more flexibility? The framework can, for instance, try out a few different values, right? This is typically done in the first mini batch. If you see, a lot of values will be very high because the framework is trying to figure out what is the best parameter I can use to run this configuration, right? So by doing it at runtime, it gives you the maximum flexibility, or it gives you the maximum benefit. So that's why it's not it's not C, where you do it dynamically but at compile time. You want to do it dynamically at runtime, right? So that you get the best out of it. It's the most flexible if you want to think of it that way. Does that help? If not, I will also point you to tf.data.autotune, which will tell you a little bit about what this does behind the scenes, right? Let's see, where is the auto tune part. Yeah, I think you have a lot of details there, but you don't need the details. I think you'll see a lot of these diagrams that were used in your own course slides, but you will, there's also a separate documentation page from the API documentation, and you can also check that out. I think that also has some more details, right? Yeah. So is it better now? Do you understand why it's option A and not the others? Okay, great. Let's move to the next one. Which data type is returned by TensorFlow datasets? NumPy arrays, NumPy list, tensors, none of the above. B, C, okay. Any other answers? Okay, let's take a look at the answer. It is tensors. Again, you will remember from last time that a lot of NumPy things are not very GPU friendly, right? And for this reason, a lot of libraries choose to operate with tensors. That's the only reason. So tensors is what is returned by TensorFlow datasets. Okay, let's move to the next question then. What is the advantage of using distributed training in TensorFlow? Easy to use, minimal code change, better performance. C, 2 and 3. Okay. Is 1 not true? Is it not easy to use? Okay, let's look at the answer. It is 1, 2 and 3. If you remember going back to distributed training, the slide that I was talking about, saying this is not why distributed training, but this is talking about tensor flows distributed training. It's basically easy to use, great performance and versatile, right? So now if you go back to the question, yeah, easy to use and minimal code changes and better performance, right? So D is your correct answer. It has to be easy to use from a framework perspective, right? If it's very difficult to use, even if it's 2 lines of code that are very, very difficult for you to write, think about it. Would you consider it an advantage? Is this one also clear? Okay, let's move to the next one. Which of the statement is /r true about tensors in TensorFlow? All tensors are immutable, all tensors are mutable, some tensors are immutable, none of the above. C, some tensors are immutable, okay. A, all tensors are immutable. Okay, let's look at the answer. It is all tensors are immutable, right? So if you worked with Python, you would have seen that in Python, a lot of numbers, all numbers and strings are immutable, right? What does immutable mean? You can never update the contents. You can only create a new one. You can have a copy, but you can never really update the contents. So a tensor is the same thing. It is also immutable. You can never update it. You can only create a new one. Now here's a question, open-ended. I won't answer this, but think about it. Why is this needed, right? Let's even forget about tensors. Why do you think numbers and strings are immutable in Python? Any answers? Have you thought about that? Is that interesting? Okay, it's interesting, I'm guessing. Due to memory address. Okay. Why would that need to be immutable? So let's say I have a variable, right? And that also has a memory address, right? Why does some things like numbers and strings have to be immutable? The memory address is not really unique to numbers and strings, right? Everything has a memory address. Think about it. It's fine. You don't have to answer it today, and it's not part of your course questions. It's just for curiosity. Go look it up if you're interested. But let's move forward. So yeah, we have about half an hour left. So I'll again ask, are there any doubts or questions that haven't been spoken about so far? From week 1 to week 5, are there concepts that are not clear, that you find it very difficult to answer questions about, or anything like that, right? We can take it up and discuss it. The sooner you do this, it's better. A lot of people come with a lot of questions in the final session, but again, that's the last session, right? So I can only take so many questions in the 2 hours. So the sooner you guys start looking through the material and seeing where you have doubts and questions, the sooner we can get them cleared. And that way it gives you also time to go back and look at what I've said, think about it, and see if you have follow-up questions. So we are already kind of getting to the midpoint of the course. So I would definitely encourage you to go through any questions that you have, right? Whenever you watch lectures, it's always good to keep track of your doubts or your questions, and that way you can just post them on Monday, and then I'll answer them. And even if it's slightly outside the scope of the course, let's say you're looking at some FPGA, or you're looking at an ASIC and you're curious about something, feel free to ask, right? We usually have 5-10 minutes extra left over towards the end, and I'll be happy to take up questions like that. Like today we spoke about dragonfly topology, right, which was not really part of the course in detail, but I'm happy to do that. So feel free to come up with those questions. Okay, if there is nothing else for now, let's move forward. Which of the statements is/are true about sequential API in TensorFlow? More flexible than the other 2 APIs available, can handle models with nonlinear topology, can handle multiple inputs or outputs, groups a linear stack of layers. Any answers? Think about it, take your time. So a lot of these concepts may be very abstract, right? So the simplest thing you can do is to try out some of the code snippets that are discussed in class using the sequential API and functional API, and that will give you a lot more clarity. C maybe, okay, can handle multiple inputs or outputs, okay. Anyone else? I'll wait for a few more seconds. Okay, let's take a look at the answer. So it is groups a linear stack of layers. So let's go back to our very first part here. So in this 3 ways to create a model, for example, in the sequential API, you had this example where there was a convolutional layer followed by a batch norm followed by a ReLU, right? So this is technically stacking a group of layers. Whereas if you look at the functional API, you will see here that this network kind of branches, it diverges and then it converges, right? It's not really one linear sequence of layers, and functional API is able to handle that. And if you recall in your lecture, it was mentioned that sequential API cannot do this. And similarly, if you have multiple, so here for instance, this output of this first layer is going to 2 different layers, and then here again this is going this way, right? So things like this are typical of functional API but not really of sequential API. So going back to the question now, can handle multiple inputs or outputs? No. Can handle models with nonlinear topology? No. Groups a linear stack of layers? Definitely yes. So you need not even think about this, right? More flexible than the other two APIs. This is the answer. Hope this is clear. If you have any other doubts, feel free to ask. If not, let's move on. Do you need to recompile code written using TF-XLA after shape changes in the code? Every time after shape change, not needed. Depends on the nature of the code, none of the above. Any answers? A, every time after shape change. Okay. Anyone else? I'll wait for a little longer. Okay, so it is every time after shape changes. So if you remember, the XLA compiler requires shapes to be fixed. So the moment shapes change, it recompiles. So if you think about why this is, there are optimizations that are dependent on this, right? So if your shape changes, certain optimizations might change, which is why it recompiles. The moment your optimization changes, so you always want to get good performance, right? So a lot of these things change, or sometimes it can even break functionality. That's why the compiler will require that you have to recompile it once the shape changes, and this can add unexpected latency. So again, looking at the options, not needed is not true, depends on the nature of the code is also not true. Every time shape changes is the correct answer. Hope this is also clear. Any doubts here? Okay, let's move to the last question for today. Which of the following is not true about auto clustering? Predictable behavior, fully automatic, weird performance cliffs, none of the above. B, fully automatic. Which of the following is not true? Notice the question carefully. A, predictable behavior. Okay. A, predictable behavior. Okay, let's look at the answer. It is none of the above. Okay, let me just look at this. So predictable behavior and weird performance cliffs are definitely contradictory, right? So if it is weird performance cliffs, which it definitely is, then it cannot be predictable behavior. So predictable behavior is definitely not true. This answer needs to be changed. So the official answer key from NPTEL says none of the above, but I don't think it should be none of the above. It should be, as you guys correctly said, it should be predictable behavior. Fully automatic is correct, so it is true. Weird performance cliffs is also true. Predictable behavior is not true. So that's the correct answer. So any idea why there would be weird performance cliffs if you used auto clustering? So just as a recap, auto clustering tries to find the largest compilable blocks and then automatically um, compiles those using XLA, right? As opposed to you manually doing this. So why would that cause unpredictable behavior or weird performance cliffs? Any answers? No answers? Okay, you can think about it. Again, it's just asked for curiosity's sake because we discussed this as part of the course. So you might wonder, right? Why is this so? So if you do think about it, try to find out the answer. And if you have answers to some of these questions I ask in the next week, remind me saying I looked at this, I couldn't find it, or I still am curious, I want to know, then we'll talk about it. But if not, that's completely fine. You don't have to go through these. So I think this was it. Yes, this was it. So today we are well in time. It's 8:40. So in case you have questions, feel free to ask. I will stay on the call maybe for 2 to 3 minutes, depending on how many questions you have. We could even do 5-10 minutes if you have questions. But if not, then feel free to leave. This is all I had for today. So thank you so much for joining in and for interacting, and I look forward to seeing you next week as well. But if you have questions, please ask them. Even if I don't have slides today, I'll definitely get back in the next week, and preferably with some examples that will help you understand easily. So ask me in case there are any questions. I'll wait for a couple of minutes. If you have no questions, please free to drop off. How can I watch the next week's video? So if you're talking about the course lectures, they're already live. Week 6 content I think went live yesterday. So you can just go to the course page and check it out. If you're talking about the live session, this will be at the same time next week as well, 7 to 9 p.m. on Monday. So you can log into the same link at the same time, and then that will give you access to the live session. Does that help? Okay, great. If you have no other questions, then feel free to drop off. Thank you.